So the AlphaChip was designed in like few hours compared to the traditional approach of few weeks. Is that like 6 hours is the magic?
We designed a neural network that can generalize across the different layouts. And then it's faster, right? Because it uses what it learned from before, right?
A revolutionary breakthrough in chip design powered by AI. A process that could take months or even years can now be completed in just a few hours. That is AlphaChip, developed by researchers at Google Brain.
Right now, it takes more than $100 million, maybe into the billions, to train a massive language model. And then at inference, the costs are really low, less than a cent or a fraction of a cent.
For decades, chip design was a game played by only a few. It required deep expertise, expensive tools, and years of experimentation. But when AI can learn from thousands of previous chip layouts, when design intelligence can accumulate and improve over time, the rules of the semiconductor industry begin to change. The semiconductor race today is no longer only about factories and capital investment. It is a race to master design intelligence. So could AI-augmented chip design become the most viable pathway for emerging nations to move deeper into the global semiconductor value chain? And if so, where should Vietnam position itself in this game?
This is a chart of connectivity. This is the total egress bandwidth, international connection for Vietnam. It's been higher than Moore's Law since 2000 until now.
Dr. Anna Goldie and Dr. Azalia Mirhoseini, the two guests in this episode, were part of the team behind AlphaChip, the AI system that transformed how computer chips are designed. Both previously worked as researchers at Google, helping pioneer the use of reinforcement learning in semiconductor design. Dr. Anna Goldie is one of the pioneers applying reinforcement learning to chip design. Dr. Azalia Mirhoseini is a leading AI researcher and a professor at Stanford University, recognized in MIT Technology Review's 35 Innovators Under 35. Together, they later founded Ricursive Intelligence, a Silicon Valley startup that raised a $300 million Series A round just 4 months after launching, reaching a valuation of $4 billion.
Thank you for joining us today. So the world is amazed by your recent development of the AlphaChip, and we learned that you guys apply reinforcement learning into the product. So can you share a little bit about how reinforcement learning is applied in AlphaChip?
Yeah, so we kind of treat chip design, like the layout of chips, like a game. So it's like if, with AlphaGo, like you learn how to place the pieces to win the game.
Like a chess game?
A little bit like a chess game, except now instead of, an 8x8, you have like, arbitrarily like hundreds by hundreds, and you have millions of pieces.
I see.
And then, reinforcement learning, it's basically like you try placing things and then you get punished or rewarded based on how well you did, so you can learn to do better.
Right. So is there any gamer in your team?
Yeah. I like to play games.
You play games?
Yeah. I like to play like strategy games. Like,
okay, so that's why you apply the strategy game, your hobby, into the new product.
That's right.
Okay. So it also like described as the alien-like for the layout. So how can you imagine what it looks like, especially for something that never happens in the world before? Is that because you read some kind of books, or like you listen to radio, you have an idol, so something like come into your mind, something that never happened?
I think so. With the alien-like designs, it's more just like humans would never imagine laying it out like that, right? But the AI can discover on its own that this is actually more efficient. So, you know what I mean? Like people have certain preconceptions of how you should do things, right? And then, but if you look just at like the quality of the final layout, certain new design policies emerge.
AI and semiconductor, something is really not familiar to most people. This seems fascinating about the terms, but they don't really understand what it is.
Chip design is a very complex process, right? It's like maybe it takes 3 years to go from the idea of a chip to a final product. Let's say you're looking at layout optimization, like what we did with AlphaChip. Yeah, it's almost like you're designing, like it's like something like a game, like or like even a city. Like you're trying to figure out, how can I place the pieces? Like as a kid, it's like you're playing with your toys. How can I place them such that I meet all of these rules, but certain, like maybe this guy likes to is friends with this other guy, they should be near each other so they can talk. Yeah. But it's just very complex version of that.
Right. What is the biggest misconceptions about AI that people usually, tell you?
The biggest misconception, I think, is that it's magic. Something like that, right?
Magic.
It's magic.
It's magic.
Will do it.
It's come from nowhere, right? But actually, it's the hard work of a big team, right?
It's hard work of a big team.
Yeah.
There's a lot of pain and like tears and sweat that goes into like making it.
So the AlphaChip was designed in like few hours, like 6 hours, right? And compared to the traditional approach of few weeks, is that like 6 hours is like a magic that your team is prepared ahead, like something the magic that you target on, or like it's just something surprised you guys?
I think we were a little surprised. So one of the ways that we could make it much faster. So originally, whenever we saw some new chip, we would take a neural network, we would train it from scratch. Like it doesn't know how to do anything.
I see.
And then we train it, and it takes like 48 hours.
Right.
But what we realized is we want to like learn from experience, right? Like let's say you're a human, you place a chip, you place a different chip, you learn things, right? And then you see a new chip, you can do it faster.
Right.
So that's like how we designed a neural network that can generalize across the different layouts. And then it's faster, right? Because it uses what it learned from before, right?
So 6 hours is not the limit for the AlphaChip. So you guys were gonna have like different versions of AlphaChip, so have a less time for producing it.
I think actually in our Nature paper, we show a plot. We show, okay, how much time you spend on this particular chip, right? And then how much data you learned from in the past, right?
Right.
And so you can actually generate placements in like 1 second, right? No experience on that chip, but they're worse, right? There's a trade-off. But the more experience you had in the past, the better this zero shot, like 1 second layout is.
Yeah, 1 second layout.
So if we can get more experience.
Yeah, and the more experience, the less time that it required to produce the AI chip.
Yeah.
I was curious about the materials that you guys use for the AlphaChip. Is that the materials is different from the normal chip right now, or like you apply totally new kind of materials?
We use like normal like semiconductor
silicon,
material. Yeah, silicon,
germanium, and graphene. That's what you use for the AlphaChip.
So that's not a dimension that we were modifying. But I've seen very interesting work, photonics-based chip design, those kind of things. Like actually one of our co-authors, Richard Ho, I think he worked at like Light Matter doing photonics-based.
What type of materials will be for the next generation of the semiconductor?
I mean, I think I'm not an expert in materials and chip design, so yeah, maybe photonics-based is a future direction.
Yeah, that's all about the voice talking about.
Yeah.
About the new materials for the AI-driven hardware. Right? To your perspective, what is the greatest turning point of the history of the AI that you feel like it really shaped the industry to the status we are right now?
I think so. One of the moments was like AlexNet. So there was this vision model that was suddenly able to do like image classification much better. And the whole world was shocked. And I think people thought it's not even possible, right? Because there's all these humans, they're so brilliant, they make these custom rules to do vision. And suddenly there's this neural network that, no specific human design was put into it, but it could discover these categories and do better.
Yeah.
So I think that shook the world,
It shocked the world.
Yeah.
The semiconductor value chain consists of multiple stages from design, simulation, and optimization to fabrication and packaging. Among them, chip design is where the highest intellectual value is created. Unlike manufacturing, chip design does not require tens of billions of dollars in factory investment. It requires people, mathematics, algorithms, and the ability to learn continuously. At a time when technology is accelerating at an unprecedented pace, Vietnamese companies are shifting from outsourcing toward creating higher value innovation.
Thì mình nghĩ cái phần mà Việt Nam có thể tiếp cận được là phần chip design, không phải là cái phần sản xuất cái chip trực tiếp, bởi vì phần đó cực kỳ là cạnh tranh. Và Đài Loan nó đi quá xa rồi. Nhưng mà mình nghĩ là làm về thiết kế thì là cái chi phí nó rẻ hơn. Bởi vì chỉ là làm phần mềm thôi. Bởi vì thật ra cái công ty Nvidia nó thành công không phải là nó sản xuất chip mà nó là thiết kế chip.
These applications show that AI is increasingly becoming a foundational capability, enabling humans to simulate, optimize, and control ever more complex systems. And it is precisely this capability that allows AI to move deeper into the highest value stage of the chain, chip design. The global semiconductor industry is projected to reach revenues of $1 trillion by 2030. Alongside this growth, demand for AI and semiconductor talent is rising rapidly worldwide. Vietnam is gradually integrating into the supply chain, from design and manufacturing to chip testing and packaging. To achieve this, education and training become the key driving factors.
We are expanding collaborations with over 65 universities in Vietnam, including Hanoi University and Ho Chi Minh City University. And the goal is to add or integrate AI education and semiconductor curriculum to the program.
In that context, the role of education becomes even more critical. From an educational perspective on AI and semiconductors, we continue the program with insights from Dr. Azalia, co-founder and CTO of Ricursive Intelligence and a leading professor at Stanford University.
Thank you for joining us today. So Vietnam is trying, it is in the major steps in its efforts to join the global semiconductor supply chain. The whole country is so excited about their new role in the industry.
I really admire that because when I put my thoughts around how future of AI is going to look like, think about any kind of transaction, any kind of software program, any kind of data process, and everything is going to be done either entirely by AI or increasingly by AI in the next few months. And all of these AI algorithms are going to need chips to run on.
Yeah.
So semiconductor and chips are becoming more and more important every day as AI becomes more capable. The importance of semiconductor and chips become even more evident.
Right. Semiconductor is actually the foundation of the entire modern technology ecosystem. So that's why the combination of semiconductor and AI has led to many breakthroughs. And what breakthrough is the most exciting to you?
In general, in AI or in AI and semi?
Yeah, in AI and semi.
Of course, I'm biased, but our work on AlphaChip, it was a very exciting moment because we kind of for the first time showed that we can train AI models that can become more and more experienced and better at the task, at this specific task in chip design, which was layout optimization, as they solve more instances of the problem. So just like humans, like a physical designer or other chip expert, as they solve more problems, they accumulate experience. And then they become better, faster at solving new problems. And with this AI that we developed and with this deep reinforcement learning and pre-training approaches, we showed that we can have the AI take the same role. That is a new opportunity because AI, unlike humans, can have access to infinite or increasingly large amounts of compute and use all of that to learn more from experiences, become better, become more generalizable, and solve new problems better and faster. So it kind of creates this flywheel effect, which is a very exciting moment for chip design.
So for chip designer, is there any bottleneck in terms of the materials, the size, or in terms of the power it consumes?
Yeah, there are definitely challenges in terms of how much performance we can get from chips given a certain cost or energy that we are willing to pay to design these chips. So there are different kinds of constraints. Part of it comes from the materials that we use for a memory or for a logic gate or the silicon. The other part comes from the architectures that we can develop given those materials and how they serve the applications, specifically the AI applications as well. And the third part comes from manufacturing. At the end of the day, these chips need to be printed and we need to have access to them. So there are different kind of constraints and barriers that come from different parts. And one of the challenges in AI these days is, if we want to get more specific, is that companies have become really good at making chips that can process more and more flops or compute. They can do a whole lot of compute. But then this compute needs to be done on data. But a challenge is that the bandwidth, the memory bandwidth, is not progressing as fast as compute. So the speed at which we can retrieve data and process on it has become a bottleneck in the past few years. So that would be like a more concrete example of, given AI workloads, how we are sort of constrained by the limitations of, say, memory bandwidth.
Is there any limit for the speed? Like, you think it can be, faster and faster every time you guys make a new version?
I think the chip design process, like the part from the design spec all the way to GDS2, or the thing that you send out to an external company for manufacturing, that process can become a whole lot faster. Of course, a lot of research is needed, both in academia and industry, to go from the current year-long process to maybe a month, and then maybe a week after that. But another challenge is the manufacturing, which is right now maybe 3 to 5 months and so on. So we are currently not bottlenecked by manufacturing, but it would be a great thing if that happens, if our chip design cycle is really fast and the manufacturing part is the only bottleneck. But as we saw in some of the talks today, even that, the manufacturing part itself is speeding up.
After many years working at Google, they came together to found Ricursive Intelligence, an AI startup with a bold ambition to automate chip design and to enable more companies, even more nations, to participate more deeply in the highest value segment of the semiconductor industry. If chip design can be automated, if design intelligence can be accumulated and scaled, then the question is no longer who has the largest factories, but rather who can master design intelligence. During their recent visit to Vietnam, they explored Hanoi and openly shared their reflections on Vietnamese talent and the country's potential. As AI lowers the barriers to entry, as knowledge can be learned, shared, and accumulated.
So what do you think about Vietnamese people with your first impression?
They're very nice and friendly. That being said, I've been exposed to Vietnamese people a lot back in the Bay Area. So there's a lot of Vietnamese exposure in the Bay Area as well.
And actually, most of Vietnamese people study abroad. They really focus on technologies and coding and mathematics.
Yeah.
Competitive advantage begins to shift toward people, education, and the ability to build an open learning ecosystem. And to better understand the role of education, academia, and design intelligence in the AI era, Momentum continues the story in the next segment.
How the research work different from an industry player compared to the academic institution?
So I should say that in academia, doing research in chip design specifically can be harder, because having access to these technologies and PDKs and EDA tools, they all are very hard and very expensive. And academics always work on lower budgets, right?
Yeah.
But at the same time, one of the roles of academia is to train the next generation of AI people or chip designers and so on, or systems engineers, so that academia can play a big role there. And also, I think there is still a lot of interesting work on the, AI for design, engineering, coding, and such that we can do in academia with much lower, fewer resources.
Any of them become commercialized recently?
I think the work that we did on inference time scaling, I gave a talk earlier, we are seeing glimpses of that in frontier models. Of course, they came up with that with similar findings as us simultaneously, but we are continuing to push on making AI capable AIs for various sorts of engineering tasks, and we're very, very excited to see a lot of interest. For example, the work that we did on kernel bench is this evaluation benchmark for seeing how well AI can program hardware. We saw that several companies like NVIDIA, like Sakana, other started like evaluating and benchmarking on those, so we can have impact in many different ways in academia.
Very exciting. What did you see the collaboration between the academic institution and industrial players in the field of AI and semiconductor evolving in the next few years?
I really hope that the ties will strengthen, because academia, the best asset that we have are the bright students who are going to develop the future of this field. I think we discussed a few ways that can happen. For example, a lot of progress in AI happens with benchmarking, because if we have a benchmark, then it's much easier to develop AIs that do well on that benchmark, and that helps with progress. But what I'm hoping to see is that, at least on the benchmarking side, like academia and industry can collaborate, show or make new kind of evaluation benchmarks that then everyone can work on and help each other make progress faster. The reason the industry can help a lot, because those are the ones dealing with these problems day to day as they're building their chips.
And they have capital resources.
Yeah, exactly. Yeah.
Sure. It is like any special educational background should be important for them joining the team in Stanford. And mathematics major is like...
Yeah, I think we hire
Definitely.
people from math and CS and EE and maybe even physics and so on. I think at Stanford we are lucky, like we get a huge number of really amazing applicants that have done something amazing even before starting like their PhD program. With the wealth of tutorials and videos and all that on AI and also on hardware that's out there, really there's an opportunity for everybody to educate themselves, maybe do a side project, or like if they're truly interested in this area, there are a lot of opportunities to learn and make progress.
What do you think about if AI can create another new AI? So that could be possible, and if it's possible, then could it become the super brain or something that we cannot control?
I mean, if we call this like self-improving AI, we are already seeing that, like this kind of cycle of AI generating, and again, I mentioned some of that in my talk, in our project. So AI can make a lot of mistakes, but it can eventually overcome those and like solve very complicated problems. Then you distill back these like solutions back to the model. Next time it becomes better at solving maybe harder problems.
But it's a better version of that AI. But I mean, like if AI can manufacture or produce another version of AI, another AI.
So I was thinking like it can have a flywheel effect, because it can keep getting better in different dimensions. So it becomes the new AI is and a significantly improved version of the current AI, right? I think AI is only going to improve its capability, but I'm very excited and feel very hopeful about the future, where it kind of brings a whole lot more value and enables a whole lot more people to do things they could never do before, reduces cost and all that. So I think we're kind of in a very exciting time for the future of self-improving AI.
So have you ever observed any unexpected behavior?
Especially if you're using like techniques like reinforcement learning or showing a reward model. AI is very good at this thing called, like these algorithms do this thing called reward hacking. If you're making an AI to optimize for a reward, but improving this reward might kind of impact other things negatively. Maybe as human, you have a better idea if you're optimizing for an objective. You kind of want to maintain the general goodness of the model, right? Of whatever you're designing. But AI is not, like it can just go for that reward and kind of like really negatively impact everything else that it should be good at. So this is called like reward hacking. And models are good at that. Because they're really like, you give me an objective, I'm going to only optimize for that, right? Then it's like we have to be careful as developers and users of AI when we create safeguards and ways to ensure that the model behaves as expected as possible. And if it makes mistakes, it's not too damaging to whatever task we have.
Google already implemented 7 ethical rules and standards for AI development. So Stanford, do they have applied the similar standards for developing AI?
I think this needs to be asked from the experts at Stanford on policy, and because Stanford does a lot of excellent work. There's a center called Human AI Interaction, HAI, at Stanford that has been very instrumental in designing and implementing a lot of these policies around AI. A lot of our work is around engineering tasks, so we are less dealing with AI that has to do with human interactions and such. So we are just make sure that our AI does the software engineering, coding, and such tasks that they have as good as possible.
If a semiconductor can talk, you think what type of complaint it should have towards how human is using it right now? I'm too busy, I'm too tired, that you guys...
Yeah, I think they are busier than before, meaning that the type of AI workloads that we have utilize more and more of the hardware than before. But maybe bad news for them and good news for us is that we are going to increase this utilization. So they're going to be busier. But the good news is they're going to help us run AI and make AI more and more useful.
Thank you so much for sharing with us your insights in the AI and semiconductor field.
Thank you so much.
Thank you so much.
Thank you.